Today we're going to take a look at more direct proofs and proofs using the contrapositive. In doing so, we're going to talk about the real numbers, and then later we'll talk about sets. So first up, real numbers. So here's some basic facts that we know about the real numbers. We know that if we square a real number, the result is greater than or equal to 0. We know that if we take an even power of a real number, the result is greater than or equal to 0. And we know that if we take a negative real number and take it to an odd power, then the result is going to be negative as well. So these are some basic ideas that we'll be able to use throughout our proofs. So here's an example of something we might want to prove. So we have two real numbers, x and y, and we're going to show that if xy equals 0, then x equals 0 or y equals 0. This is a fact that you've used throughout algebra, but you have never shown that it's true. So here we have we're going to assume xy equals 0, and we're going to take two cases. Either x is going to be 0 or it's not going to be 0. And the reason we're going to take these two separate cases is because the behavior of x as 0 is different than as it being not 0, and we'll see that in our proof. So when x is 0, we have the result. So x times y equals 0, and x was 0, then x is 0, so our conclusion's there. So the more interesting case is when x is not 0. When x is not 0, then we are assuming that xy equals 0. So we can multiply both sides of this equation by 1 over x. And when we do so, on the right-hand side, we'll end up getting 1 over x times 0, which is 0. And on the left-hand side, I'll get 1 over x times y. And 1 over x times x is 1. So this is really 1 times y, or just y. So setting my left-hand side and right-hand side equal to each other again, I get the conclusion that y equals 0. So when x is not 0, y is then 0. So now I know that if x times y equals 0, then x equals 0 or y equals 0. Now here's another result that I might want to prove. I might want to have x be a real number, and I want to show that if x cubed minus 7x squared plus 3x minus 21 equals 0, then x equals 7. Now this might look like a basic algebra problem to you, and it probably has resembled something that you've done. So we're going to write it though in terms of a proof. So to do this, we're going to first notice that my first two terms of this equation, my x cubed minus 7x squared plus 3x minus 21 equals 0, those first two terms have an x squared in common, and the second two terms have a 3 in common. So when I factor out an x squared from the first two terms, I'll get x squared times the quantity x minus 7. When I factor a 3 out of the second pair of terms, I'll get a 3 times the quantity x minus 7. Now, I have a number times x minus 7, and then a number times x minus 7. So now I can factor out an x minus 7, and when I do so, I get the result x squared plus 3, that quantity, times the quantity x minus 7 equals 0. Now, using the previous result that x times y equals 0, then x equals 0 or y equals 0, I can set both x squared plus 3 equal to 0 and x minus 7 equal to 0. Now, notice that x squared plus 3 equals 0 implies that x squared equals negative 3. And we have the property of real numbers that squaring a real number results in a positive number. So I can't get negative 3, so I can notice that x squared plus 3 does not equal 0, ever. Then I'm stuck with x minus 7 equals 0. And solving that, I notice that x must be 7, and I have the desired result. Now, the other type of proof that we're going to talk about is ones involving sets. So this is just a quick review of sets, what we mean by the intersection, the union, the difference, and the complement. We've used all of these things in previous days, so we're going to use them again today though, and this time we're going to throw them into proofs. So here's an example. I have two sets, A and B. I want to show that the set A minus B is equal to the set A intersect the complement of B. So whenever we're trying to prove equals between two sets, what we generally do is prove two set inclusions. So this proof follows that model. We're going to show that A minus B is a subset of A intersect the complement of B, and then we'll show that A intersect the complement of B is a subset of A minus B. And once we've shown that they're both subsets of each other, then there's no option left but that they are equal, and we will have shown the result. So let's first look at A minus B is a subset of A intersect the complement of B. So it's very common when you're doing set proofs also to take a generic element X in the subset that is in the set that is the subset. So here we have X is an element in A minus B. Well, then we think about what that means about that element. Well, it means that X is in A and it's not in B. That's what the difference means. Well, now, X not being in B means that X is in B's complement by the definition of our complement. So we have X is in A and X is in B complement. Well, another way that we can write that is X is in A intersect B complement. And in doing so, we've shown that an element that's in A minus B is also in A intersect B complement. Now, let's think about showing the reverse. So I'm going to take a generic element Y that's in A intersect B complement, and I'm going to show that it must be in A minus B. So Y is in A intersect B complement means that Y is in A and Y is in B complement. Well, Y is in B complement means that Y is not in B. So now I have Y is in A and Y is not in B. And I can use the definition of the difference to say Y is in A minus B. So now I have that A intersects the complement of B is a subset of A minus B. And because I have my two subset inclusions there, then I have the equality that I was going for. So here's a set proof paired with a biconditional. So let's take a look at the idea that with A and B being sets, then A union B equals A if and only if B is a subset of A. So with a biconditional, we need to show the two directions. So first we're going to show if A union B equals A, then B is a subset of A. So to do this, we're going to use the contrapositive. It's really common when you have equals on one side and a subset on the other side that you go with the subset option if you can, and a lot of times that means using the contrapositive. So here we're doing that. So we're going to assume that B is not a subset of A. So that means that there's some element in B that's not in A. So I have this element X. Since X is in B, then X is also in A union B, but it's not in A. So that means that there's an element in A union B that is not in A, and therefore A union B does not equal A. And I have the contrapositive proven. So that takes care of that direction. Now we need to look at the converse. So we have if B is a subset of A, then A union B equals A. Now again, here I have the subset is with my if, so I'm going to assume that. So I'm assuming that B is a subset of A. So to show that A union B equals A, this is equals with sets, so I need to do the two subset inclusions. So I'm first going to show that A is a subset of A union B. So This, just from the definition of union, is true. Now, I'm going to show that A union B is a subset of A. This one has a little bit of work to do. So I'm going to take an element, y, and say it's in A union B. That means that y is in A or y is in B. Now, if y is in A, then we already have our result. But if y is in B, then we need to take the step of saying, well, y is in B. Since B is a subset of A, that means that y is in A. And therefore, A union B is a subset of A. So A union B equals A. And we've proven the converse is also true. And therefore, we have our entire biconditional.